Let us do some partial question on AC, alternating current, so that you are familiar what type of question you are likely to encounter. Okay. Okay, let's try that. An alternating current supply. There's an alternating current supply connected in series with a resistor R. The variation with time measured in second of the current measured in ampere in the resistor is given by the expression that for the current in the resistor R, determine the frequency. What is your answer? Can compare with the standard formula. You can get it from data sheet. Data sheet use X, you use I. Then omega is 2 pi F. So 2 pi F equals 380. So F is 380 divided by 2 pi 60 hertz. Okay.
Okay.
Root mean square current. What's your answer? Root mean square current. Peak divided by root 2. Yeah. Peak value is your peak or maximum value divided by root 2. Can get.
Yeah.
To prevent overheating, the mean power dissipated in resistor must not exceed 400 watt. Calculate the minimum resistance of R. Yep. What is your answer?
7 square times R. Okay, yeah.
And use your I square R. Here we require it to be minimum
8.16.
8.16. Let's see. Minimum resistance, thus we have a peak current. Right? R minimum. That one is given. R minimum. There is a peak current. No,
Oh,
4.1.
wait, I square.
Where do you go?
Which I value you use? Okay, okay. 9.9. Okay.
Minimum resistance. Minimum
Mm,
resistance, we want the peak value. Right? We cannot use root mean square value. Peak
okay.
value, it will break down. Okay or not?
Yes.
Okay. Usually, it's easy to set AC because you can test two things. You can test AC together with electromagnetic induction. And electromagnetic induction, two topic, counting. Okay, that's why we cannot answer, we cannot do the question. You haven't learned electromagnetic induction yet. So let's try something else. Yeah, you can see that all these are electromagnetic induction and right? This one is oscillation. Right? They use induced current. Okay, how do you connect this? Complete the circuit in figure 5.1 by showing the connection of the supply and of the load to the diodes. Right? Supply connect to here, where, where the arrow and the arrow there, that point and that point. That's where you have the rope, where the two arrow meet. Okay, this is not join, join is a dot. Join is a dot. Okay or not?
Yes.
Okay. Suggest one advantage of the use of bridge rectifier rather than a diode, single diode for the rectification of alternating current. Yep.
Ish. Instead, I don't really know. I forgot already. Uh,
You use two both cycle, so double the power supply on every half cycle. Whereas single diode is what, half cycle only. This is both half cycle, both half cycle, there's rectification, and so the greater average or mean power. What is meant by smoothing?
reducing the what's it called? Reducing the fluctuation.
Reduction in variation of the output voltage. You want to make the
Oh,
output voltage constant, uniform. The effect of the value of capacitance of the smoothing capacitor in relation to smoothing. Yep. Large capacitance, larger capacitance produce more smoothing, or you can say
okay.
that the product of RC is larger for the same load. Right? Larger capacitance produce more smoothing for the same load, or you can say that larger capacitance produce more smoothing, product of RC large. Right? The time constant is large. Okay.
Mm,
Okay. We have gone into example to show you about AC. This is normal in the syllabus. Okay, let us start magnetic field. Topic 20. We have covered all this. We are now in topic 20. We have covered topic 21. Topic 20 tend to be a bit larger lah, because it combine electromagnetic induction and charged particle together lah, in magnetic field lah. And we still, after finishing that, we still got three more topic lor. Okay, so under electricity and magnetism, we got electric field, capacitance, rotating current, magnetic field. Okay, under magnetic field, page 156, concept of magnetic field. How is it produced? Produced by magnet or current carrying conductor. Represent magnetic field by field lines. Okay, we go into that. You study in your O level. Force on current carrying conductor. That's a formula that you need to remember. And then Fleming's left-hand rule. And this is to measure, this setup is to measure B. Force on moving charge. That's the formula that we will encounter. That's a formula. And then this is the most common one that will come out. Magnetic field due to current, long straight wire, flat circular coil, long solenoid. Okay, that's the field due to the long straight wire. How do we get the field? Using a grid rule and solenoid. How do we get the field? Don't worry about the formula. Formula not required, but you need to know how to use it. And then ferrous core concentrate the field. Here's your flat coil or circular coil. That's the formula. Know how to use it, don't need to memorize it. Know what the symbol stands for, that's good enough. Electromagnetic induction. Concept of magnetic field is developed by studying the force on current carrying conductor and on charged particle in magnetic field. Hall effect is studied as example of the use of magnetic field. Previously, there's MRI lah. Now they throw it away. There's under medical under application now. Right? G, you likely to use it. Hall voltage, you need to know how to derive it. That's a syllabus. Understand magnetic field is example of field of force produced either by moving charge or permanent magnet. Represent the field line, magnetic field with field lines. Right, this is just for info. No need to study much. I thought if it teaches magnetic field, there's no uses, no point also. So electromagnet to lift heavy object, loudspeaker to convert electrical energy to sound energy. This is Millikan's experiment. Determine the charge on the oil drop, and to show the charge is quantized. This one we study. This is called the velocity selector, used together with electric field and magnetic field to determine the charge to mass ratio. Right, so this one determine the charge. This method determine the charge to mass ratio. So from there, we can calculate the mass of the particle. Magnetic field is an example of the field of force. Few lines of current carrying conductor using iron filing. Then you can show that there is something around the current carrying conductor by iron filing, or using a magnet. Can show that these are the lines. Few lines of bar magnet using iron filing is produced. The thing we need to remember is magnetic field is produced by current carrying conductor or by permanent magnet. Okay, review your lower form work. There are no individual magnetic pole or magnetic charges. electric charges can be separate, but magnetic poles always come in pairs, north and south, right? But of course, scientists will be trying to separate that lah. North separate and south separate lah. But so far, I don't think there are any success lah. So the properties, opposite poles, north and south attract, north and south attract, or south and north attract. Right? Unlike pole, like pole, north and north repel, south and south repel. Right? Like poles repel. Field lines show the presence of magnetic field. You put it on a small table or bench, and then put the magnet there, sprinkle iron filing, and then tap the bench. Then the iron filing will follow the lines, magnetic field lines. Right? Field lines can be shown by sprinkling some iron filing around the magnet and then tapping the bench. Or we can use plotting compass, a small compass. We can mark a point here, mark a point here. Then after that, put another compass there, mark a point here, mark a point there. Okay, this is not a good diagram. Right? This one is too close together. Magnetic field line or lines of magnetic force of a biomagnet starts from north. It starts from north because we use North Pole as our convention. Starts from north and ends on the south. Lines never intersect, they never cut each other. Right? Where it is closer together, stronger field. Right? This part is wider apart, so the field are weaker. Provide a way of describing the field. Right? A visual way of describing the field. Area of low magnetic concentration, area of low concentration of field lines, weak field. Right? Here will be weak field. Further away will be weak field. This one will be strong field here. They are imaginary lines. You cannot see them unless we use iron filing. Right? In one direction is tangent to the curve. Right? Tangent to the curve. Tangent to the curve gives the direction of field at the point, at this point. Right? Uniform field, they are parallel and evenly spaced. Stop me if I'm going too fast. This is a better drawing. Right? Weaker field, stronger field. How do we test the presence of magnetic field? Right? We can suspend a magnet, a bar magnet. Magnet will align in the magnetic field of the Earth. And that's why we know there's a magnetic field of the Earth. Right? We can show that if there's a magnetic field, then we have a current carrying conductor, carrying current. There's a, it will be deflected. There's a force. Right? It's larger force, it's smaller force, smaller current. Magnetic field will produce a force on a suspended magnet or current carrying conductor. Current carrying conductor will deflect the magnetic field. What is magnetic field? Magnetic field, region of space where a force is experienced by a current carrying conductor or permanent magnet. Right? It's deflected. This conductor is deflected because it is present in the magnetic field. Right? Force on current carrying conductor. Right? This is your arrow. There's a tail, there's a head. We are only interested in uniform field. This is uniform field. Field going into page, arrow going into the paper. So we see the tail, If it's going into the page, we see the tail only. Right? If coming out of the page, we see a dot, arrow coming out of the page. We see the tip or dot. Force on current carrying conductor magnitude. That's your conductor. That's your current. So in this case, the force is 0, where the current is parallel to the magnetic field. Maximum force on conductor magnitude. Force is maximum when the current is perpendicular to the field. Right? It's given by BIL, where B is your B. B is magnetic field strength or magnetic flux density. Your examiner tend to prefer to use magnetic flux density. American will just call it magnetic field. There's a conductor. Current in the conductor. There's a current in the conductor. Length of conductor in the field. Just to review, since you have studied in your O level, where direction of the force? We will come into it later on, just to test you, see whether you can still remember. That means left hand rule. Second finger is a field. Current is going down. Current is going down. Current is going down. So force is coming out. That's your length. Force is outwards. Can.
Yeah.
Right? If the conductor is at an angle to the field, right? That's your conductor. That's your field. And that's the angle there, theta. Right? You still experience a force, but a smaller force, depending on the angle. Right? That's your current. That's your angle. Angle between the field and the current carrying conductor. Right? This angle. No, this angle. This angle. The field and the current carrying conductor. Right? So if you remember, the field must be perpendicular to the current. Right? So we find the perpendicular component, B sine theta. And then put in the formula. Okay. Force is inverse. You can try it. Force is inverse. Can get it out? The thumb is the force. The first finger is the field. And then the second finger is the current. Current. Field. Current, force. It's a bit difficult to show this one. Twisting your finger. There's your field. There's your current. Force is. There's the current. Okay, can? Anyway, we
Yes.
go into it. Direction of force on current carrying conductor placed in magnetic field. Direction of force on current carrying conductor placed in magnetic field can be found using Fleming's left-hand rule, or some rule, call it motor rule, or right-hand palm rule used in Australia and New Zealand. Palm rule is easier to use because it's easier to move your palm, right-hand palm. There's your, oh, that's what I learned from the student. McDonald fried chicken. There's your force. McDonald is a force or motion. The field is the first finger. There's your second finger. Each of them perpendicular to each other. Right? Fry is the field. Chicken is the current. Right? How we memorize it? We use a thrust. Thumb is a thrust. First finger is a field. And then second zero. Second is a current. That's my time. But your students are more imaginative. Right? Motion. Thumb represents motion or force. Field, first finger represents the field. Current, second finger represents the current. Okay, let's try to use that. Okay, for this diagram, which pole is north? You are given a current carrying conductor. You are given the force. So which of these are magnet? Which pole is north? There's a current. There's a force. The force is coming out. Know how to read.
Teacher, thumb is the
Yeah. Which one is the north pole? You have to know how to read lah. The force is coming out. Current is going from left to right. So it's either up.
north pole.
Yep. Can
Is it the wait? What do you mean by which pole?
these two magnet one is south pole, one is north pole So which is the north pole? Which is the north pole?
The
This
bottom one?
good, good. Bottom one is the north pole using Fleming's left hand rule. Fleming's left hand rule. Okay. Let's just repeat. That's the palm rule. Use down under. You will find easier to use adjusting it whether Cambridge is familiar, I don't know Easy to remember because the fingers represent the few lines. You slap people is the force. Thumb is the current. Okay, sometimes you have problem twisting your finger, you can consider that. Okay, we got 10 more minutes. Okay, where is the direction of the force? North is on top, south is bottom. There's a power supply. Where is the direction of the force? Left or right? Right? The rail is fixed. The wire is the one that's movable. So you want the force on the wire.
Left.
Where? Left or right?
Left.
Left Okay, let's
Yeah.
see. Right? From here, the current will flow from positive terminal. The field will go from north to south. Go there. Right? There's a current. No,
Oh,
can the current is
can
coming
you use
out.
the left hand rule for this?
Current is coming out. Okay or not?
Yeah.
Okay. This is left hand rule. Where is the direction of the force on the wire? Uniform field. There's a fixed rail. That's the wire. Where's the direction of the force? Field is going in. Field is going in.
Uh-huh.
That's the length of the wire. There's a current flowing. Yep. Direction of the force.
Is it a left or right question?
Left or right only. You got one
I'm saying left.
is coming down. Here. Field is going in. So it's left or right only. It's to the right. Where did you go wrong again?
Wait.
Can or not?
Oh, okay, okay.
Make sure. Make sure you
Wait,
know
teacher,
how to get the direction. This one will be
teacher,
tested.
teacher. The index finger is the current, right?
The first finger is the current, no?
The
Sorry,
index finger.
the second finger. The thumb is a force or motion.
The index finger is the current.
Okay, now what is the
Is
problem?
it?
Eh? First finger, force. Second finger, current. Thumb is the force or motion. Yep, can.
Yeah.
Okay, next thing is we need to define B. We use the formula, this formula. Magnetic field strength or magnetic flux density is defined as the force per unit length per unit current on a current carrying conductor placed at right angle to the field lines. That's our definition. Force per unit current per unit length, and the force, the current must be perpendicular to the field lines. Right? Force is unit, force is in Newton, current is ampere, length is in meter. So we give you a special name, Tesla. Name of a person, capital T. Right? It's Newton per ampere per meter. Right? So 1 Tesla is a unit of magnetic flux density of a uniform field normal to the wire carrying a current ampere, giving a force per unit length of 1 Newton per meter. Right? Basically, we are just using the formula of 1 Tesla, length 1 meter, current flowing is 1 ampere. That's all. I think they will accept it like we write this way. You don't like writing it so much work, this will be acceptable. Right? So measuring B, to measure B, we need to determine the force acting on a known current carrying conductor, the length placed perpendicular to the field, current in the conductor. Right? For electric field is force divided by charge. Right? Similarity there. Except this IL, this is Q. Right? This apparatus, this one came out. Where is the action of the force on the conductor? Let's say there's a North Pole. The one outside is the North Pole. Inside is the South Pole. Yep. Where is the action of the force?
Okay.
Upwards, so can or not?
Wait ah.
Can or not? Upwards, the force is upwards. There's one direction. Going in is a field. So the force is upwards. So
Okay.
place a current carrying wire horizontally and perpendicular to the field. Adjust until the force is maximum. Right? Adjust until you see a large value here. The force acting on the conductor is delta mg, where delta m is a difference in mass when the current is on and my current is off. The reaction force on the magnet increases or decreases. How about this example? Where is the reaction force? Or the mass increases or decreases? Push me, I push you. Lor. That's the reaction force. Action and reaction
Decreases.
is downwards. So the increase in mass, right? This is upwards. Upwards is on the wire. So the wire is pushing back on the magnet. So there is an increase in mass. So. Okay or not?
Yeah.
You can look on the YouTube lah, if you are interested in some of the things there. Force on wire is upwards. Newton's third law of motion tells us that the reaction force on the electronic balance is downwards. Explain. I think we won't bother about this one. Basically, this one tell you there's a current carrying conductor coming out. There's a magnetic field of the magnet. So there's a force there. The two fields will interact. And there's stronger field on one side, weaker field on the other side. So this field want to straighten, so you push it out with a force. You don't need to know that lah. Okay, anytime it will cut off. Right, there's the uses, application and motto. During the break, try some of the worksheet lah. Right? Electrical energy converted to mechanical energy. Which part of the motor is DC? Right? It's a couple. There's a field. There's a force.